Let's get started. Arghavan, can you come up? We're all going to sit. And Johannes, where is he? Fernando and Robin. Hi, Barbara. Please come and sit. We met ages ago.
Yeah.
Yes. So great. And yeah. Okay, here's Johannes. Good. It's okay to sit in the middle, guys. Okay, and Robin, can you come up? Yep. And Fernando, yeah. Please come and have a seat. Just come sit, and we'll entertain questions from the audience. I don't know how to lift this screen, but can we do that so we can write on the? Is it somewhere over here? Sorry. On a panel here. Okay.
If you click on it, there should be something that says bring the screen
Up. Great. Thank you very much. Very advanced. All right. Good. Do we have pens? That's the question. I don't see any here. Are they in here? Can we have
pen?
oh,
you mean
whiteboard pen?
yeah? You meant a marker.
I don't see. Yeah, markers. Sorry.
You didn't bring yours?
I didn't know that was part of my role this discussion later. Okay. Wonderful. Thank you so much. Yes. So just so we can take some notes. Okay. So we've got. I guess we've got about an hour, so we have plenty of time to have a long discussion. And I thought we could start with questions to the speakers, burning questions that people didn't get a chance to ask before, and I'll just sort of moderate that. Yes. Of course, any questions at all, but maybe first questions for the speakers. Yeah.
So I want to ask one to Johannes first. So obviously, the stuff is very complex that you're doing. Have you been able to identify sort of, with all that complexity, which parts are more important, which parts are less important? Because if you had to do everything at a very high level of accuracy, that would be a pretty tough go, right?
No, I think that's in some sense one of the big problems, and it's different for every experiment. So of course there's not one experiment. If you want to look at chemistry, you need a code that represents the chemistry well. Maybe you can get away with saying I just have some photonic mode and I assume that's a harmonic oscillator and that's enough.
Okay.
If I look at complex spontaneous emission, that depends a lot on the photonic structure that I have. I'm going to have to treat the photonic structure better, and probably the price I have to pay is to treat the molecule with less detail. So, but it's not always clear at all where to kind of draw the cutoff. I mean, we do it because we have to, but we know that there might be some effects that we're missing because we're reducing the complexity of our models. For example, we're working also on one project where we're doing basically Maxwell block, where I'm doing a mean field description, and it's very hard to get the polarities well in there. You get the Rabi splitting, but you get automatically kind of a macroscopic description. You have classic electric fields. You get all of the Maxwell equations, so you get the only modes well, that's it, but it's very hard to get dynamics between the polaritons that we know exist in experiments in there. So right now we're struggling with getting spontaneous emission, which is extremely important in these systems because the cavity modes have lifetimes of femtoseconds. To get that in there and to connect correctly between the polaritons. So I don't have a general answer. We don't know.
So, but it seems though, under those circumstances, you would need to have flexibility in terms of being able to sort of plug in, or whatever the word is, the right word, or plug in something or not plug it in, depending upon the complexity and what you needed, and that's it's something to strive for, but it's hard to do.
Yeah, that's one thing that we're trying to do, kind of compare. For example, we have this classical nuclear dynamics with non-adiabatic hopping, and we have this matrix product state code. So we want to compare in which regimes does one work better than the other, and for example, the vibrational quantization that we don't have. How important is that really? For example, we can plug in harmonic oscillators as the potentials in the classical dynamics, and then see what do we get from there, or how much are we missing.
Okay.
So we're trying to do that. And it would be nice to be able to more easily do plug and play.
So I'm going to write notes on the board just of things that come up. You guys don't have to turn around and look at all this stuff, but at the end we can have a look at those overall themes. Please, more questions?
May I ask a small follow-up, very similar to Gary's question? Do we really want the egg-laying wool pig? Because if you need all that complexity on one experiment, the results will be similarly complex, and you want to learn it.
Yeah, no, I agree.
So
I don't think that's
to go
the
that
goal.
way.
No, I don't think the goal is to do that.
Yeah.
I agree. I mean, the goal is to kind of identify for different things that you want to do what are the important components. That's true.
I think it's probably true for most of us anyway, but I think we should keep in mind that simulating it, unless it's about going to the moon, is not the purpose.
Well, I don't know. I mean, yes and no. I mean, it depends on the circumstances, right? I mean, if some experimentalist comes to you and asks you, you know, for guidance about a specific experiment, or you want to guide an experiment, sometimes, I mean, Klaus knows this. Sometimes you have to go into a lot of detail to.
No, I mean, the question is, what is the theory? This is already getting into the very general discussion, more general than probably. So maybe we can talk about it later.
Okay.
I understand this difficulty, of course, but I think this is very important because we see the problem. We are getting better in simulating things, but then we ask, okay, if you turn this little knob, you get a different result. And what did you actually do in the experiment? Why do you want to see it?
Yeah.
I think Robin had a point.
Oh, a somewhat related point is, I guess, if the ultimate goal is to do chemistry, then I think it's clear that we're not only talking about harmonic oscillating motion, you're going to be looking at very substantial displacements. And that would be, I think, the main interest, I would say, in terms of pushing this field into a region where you can demonstrate controlling interesting chemistry. And then I think a lot of practical questions come up, you know, because you typically have resonances with a cavity only at specific, so to speak, points in configuration space. What would be the next steps in order to control along an entire pathway? Can you dynamically move the cavity at the same time?
Yeah.
That's what you want to do, right? To have coupling all the way, to steer. So I think there are conceptual challenges, I think, that it goes beyond indeed just a big calculation.
Great. More questions from the audience for the four speakers this morning.
I have a question for Arghavan. So you mentioned that you don't know, or you know, how to describe decoherence in the models. Could you elaborate on that?
I know how to describe it. I don't know how to speak it. So basically, the problem is that if you have, even if you have, like let's say if you have spontaneous emission, and the model is collective, then you don't have the simplification of the collective model anymore. Because if initially your model is collective and you start at a symmetric state, then you only care about the Dicke manifold of states. But now if I have decoherence on top of it, that really increases the state space. So then if you have a situation where you have uniform everything, so all the atoms have the same sort of decoherence and then also feel the same coupling to the phonon bath, then you again have this permutation symmetry. But even with the permutation symmetry, you only can treat systems of maybe 30 spins with one phonon mode that you cut off the maximum like occupation to, I don't know, 50, which would be enough, for example, for the ground state on the ferromagnetic site of, for example, this Dicke type of model. But then this experimental system is already larger than that. So if you want to do any sort of benchmarking, you can't. It's basically very computationally costly.
But that's because you're describing the phonon bath explicitly, like quantum mechanical. I mean, like, couldn't you do it phenomenologically?
So we tried, yeah. So one of the things we tried was basically to treat the phonons on this truncated Wigner approximation and treat the spins using the discrete version. But that sort of the semi-classical treatments, they only work well when you don't have this non-Canadian term. As soon as you have this transverse field, okay, then it really depends on the type of quench you do. Things break down at longer time scales. It sort of depends on the observable you look at. So for example, one of the observables that the experimentalists measure is they do some type of an echo sequence. It's not quite an echo, but then at the end they measure fidelity within the initial state. It's like an imperfect echo, so you do a rotation in the middle. The fidelity is an observable that's very hard to get correctly with these semi-classical type of treatment. So it's a little bit, it's a bit hard to say what type of.
So what's the biggest problem? I mean, I don't understand that. What's the biggest problem with simulating this?
Basically, it's very hard to simulate on a classical computer the size of the system that it is there experimentally. And if your goal is to benchmark the system that you have experimentally, that's basically beyond what you can do. Is that
Yeah, but that's the problem that they're always facing.
exactly? So you can't, unfortunately, with the particular sort of approximate treatments that you do are not good enough for the experiments that are done at the moment. So you really do have to treat the bat. The bat is, you have to treat the phonon mode quantum mechanically, you have to treat the spin quantum mechanically. That's what makes it hard.
Yeah, so there's two pieces to that. One is the open quantum systems piece, and developing open quantum systems theory past Lindblad master equation, which is going on now. And the second piece is, how well can simulations, like we're doing, help one quantum simulator benchmark another
Sure.
quantum simulator? Because ultimately our classical computers are
That's
very limited.
correct. So
Right.
the point, what I'm saying is even in the regime that it's quite simple. So, I mean, your quantum simulator at the moment, what I am talking about is not a very complex model. So it's a model that has uniform coupling to one single bosonic mode. And all I'm saying is that if you are trying to really benchmark the system using n-body observables, I mean, okay, I can't also, let's say, because the system is collective, in principle, I don't have to measure the full density matrix. I can measure sort of n-body observables, enough of them, and then I know enough about my system. And I'm saying if just simulating those quantities dynamics correctly is hard for the current experimental system. So if you have a method, that's what I'm saying is I don't know a method to treat it well with an approximation that is valid. Basically. So we haven't been able to approximate.
So isn't the solution then to just design the experiment, to allow for higher frequencies, phonon frequencies, to limit the number of phonons you have to actually include in your simulation?
You mean you don't populate the mode?
Yeah, I don't
as much?
yeah.
Well, the point is, it's not really the amount that you populate, for example, if you're in this, so if you're close to the ground state, the amount that you populate depends on sort of this displacement operator that you have, but you also, so it's not the phonon frequency that matters, it's how much you're detuned from that phonon mode, and if you're detuned further away, then you have to couple to more phonon modes. And also, let's say so the more phonon modes you couple to, the less uniform your system is. So that makes it actually already harder. But then you can also say, oh, but I'll detune so much that I couple to all the modes very weakly, and that's an approach, but that doesn't give you a spin boson model that gives you an effective spin model. So it's a completely different speed.
Please.
I mean, you were saying earlier that it is hard to simulate in a classical computer. You said, I mean, if you have infinite computing power, it is still not possible. That it is an inherent quantum aspect that you have to say a quantum simulator or a quantum computer to address this problem.
I don't think this particular simulator lets you demonstrate quantum supremacy in particular. I mean, this particular model is not maybe the best way, but I think you should in principle, I mean, yeah, if you have many particles, eventually you probably can simulate on any classical computer, but I don't think physics will be amazingly more interesting. Nowadays, I think the reason we choose this model is not, well, initially is because it is actually in a regime that does allow you to fully benchmark the simulator, so then you can move to a regime where that is basically not possible anymore, where you can maybe trust your simulator at that point.
So along these lines, I wrote on the board here, can classical computers help bridge quantum simulators in benchmarking to smaller model cases? And that's exactly, I think, if I correctly done what you're talking about. Okay, great. So more questions? Yeah, Klaus?
I just wanted to sort of bring this a bit back to the topic of this workshop, say developing flexible and robust software. So for whom are you guys doing it? Are you doing it for yourself or for your group or for the rest of the world? It seemed to me, by listening to these 4 talks, that Fernando and Robin were closer to trying to develop it for the rest of the world by making things available. Whereas I wasn't sure about the other 2, that there was much attempt yet, because maybe it's too complex, too difficult, I don't know.
No,
But
it's that, I feel like, Eric, you said it.
I think in Johannes' case, and maybe also in the other case,
Yeah.
it may be too early.
that's right.
Yeah, you're
that's what
comparing a 100-and-something-year-old
Yes.
field to a 5-year-old
That's right.
field. Yeah, or even, I don't know, Johannes, like yesterday field. So, like it's just, we don't really know what software we need, right? DFT is from the
Right.
60s and et cetera, and the stuff we're doing now, I mean, even Bell's inequality is 82. So, like, we're just barely getting there. But I think this is an important thing to look forward for to the future, right?
Yeah, I mean, what I'm basically talking about is yeah. So I mean, where are we at this point,
Yeah, I was gonna-
right? Are we?
Well, I was going to ask particularly the same question about Fernando's stuff, about where is it, who can use it. You can elaborate.
I can. Well, our plan is to make this code available as open source in a couple of years, maybe 3 years. And our approach is, I mean, there are other codes, trying to do the same thing quite well. But I think our approach is such that, quantum chemistry is well established, has been there for a long time. They are unbeatable in describing, electronic structure of molecules, and we cannot do this better than them. And so, in my opinion, and we tried, and many of us tried, but we are not yet better. I mean, we lose in order to describe the ionization continuum. We lose the power quantum chemistry has to describe, correlative things and bound states. And so we decided to take the other approach, is just to start from their side and to add what was missing. And so our goal is to have a tool that could be, purchased or, well, not purchased because it will be open source, but, added to any quantum, not any, but a few quantum chemistry packages that are already available. And so you just download this tool, and with these, let's say, Multas or Multipro or whatever code you have, you can, in addition to calculating what is already available, you can also calculate the ionization continuum and dipole transition matrix elements to continuum states and obtain ionization probabilities, which is what is missing in this field. And in this way, I think that this will be more, people will use it more often, especially from the quantum chemistry side.
So you,
May I comment?
Yeah.
So I think one possible challenge, I think, coming, say, to the field of cold atoms and ions is that there's this, seems to me, this strong focus on looking at effective Hamiltonians, which is not necessarily, that's actually very exciting, but this makes it maybe a little bit less ideal for very broad, the type of broad electronic structure development that we've had over the years, which basically was possible because the Hamiltonian is super well defined. And it's just that sort of electronic structure approximations that one then uses to solve the electronic structure problem, that then the various combinations of tools that then go into the various electronic structure codes. But it's clear what Hamiltonian one is trying to solve. Here the situation is different. You can look at all sorts of Hamiltonians, and it seems almost like for every Hamiltonian there's a different set of techniques that one might want to use, and the question is a little bit, how easily could one generalize these things in order to develop very flexible software? What I think is very specific in the quantum chemistry community is that over the years they've developed packages that are widely used, that are very powerful for a wide range of problems, but I think it's because it's all based on something relatively basic, acknowledging one elementary Hamiltonian, just in a sense trying to solve it. And that doesn't seem to be so much the focus in this field of working with effective Hamiltonians.
I don't know, so I think it's a little bit like, there are certain techniques that you can use for many different types of Hamiltonians. So for example, these MPS type of techniques, if you're in 1D, you can apply it to many, many different problems. But then the question is, the question of, because they are limited, because they're exact, then you try to come up with sort of approximate techniques. And then those are, of course, problem specific, because in each problem, there are only certain things you have to care about and some things you can throw away. I mean,
I think my point is more, you're not trying to solve one Hamiltonian only. So
Correct.
would you write a
Correct, there are many Hamiltonians, but it's not that there's a different technique for every Hamiltonian. In fact,
but you would have
there's 5 or 10 techniques,
Yeah.
basically.
So
And
if you
they
were-
each have their regime of application.
So if you wanted to
As
write,
arguments.
so if you wanted to write software for a broad user community, would you implement each Hamiltonian that you ever care about in that code?
no, because the technique is general. The technique
Right.
gives you a structure for doing that for any Hamiltonian.
So,
Yes, but
so
still, how-
for example, in my open source code, you just change one line to get a new Hamiltonian. That's it. And it used to be you had to change a line in the code. Now it's just a line of Python, and pretty soon will be a pull-down menu on a science gateway. So that's a very easy kind of interface. Similarly, in DFT, you might choose if you're using carbon or hydrogen or whatever atom you're putting there, and then you choose what method you want. Do you want generalized gradient? Do you want local density approximation? Right? And there's some small perturbations, but it's one overall code package. So I think if I understand what Arghavan was saying correctly, is that even though there seems like there's a lot of effective models, because one method applies to maybe not all, but many of these models, you can write a more generic software approach.
I mean, I don't actually think that's so different than even electron structure, because you have various levels of approximation. You do SCF, presents a different problem than doing CI, presents a different problem than NCSCF. So there's
Also the same
complexities.
also the same Hamiltonian.
But the details, right?
The Hamiltonian is like the material. It's like what atom or what column of the periodic table are you on, or whatever it is. It's sort of similar idea. That
I would say the electronic structure Hamiltonian is universal. If you're changing nuclei, maybe, but it's a single Hamiltonian.
Understood. I'm just making an analogy. Our Hamiltonian. Do you want to
You
make an
can
analogy
also
better?
write a very general Hamiltonian that has every term and set couplings to 0. I mean, if that, you can turn every term that you can have.
You turn them on and off. Yeah, that's good.
There's also this issue of Hilbert space versus physical space, right? So for cold atoms, you have this enormity of the Hilbert space, whereas in atoms and molecules, you have the physical space, which is almost unlimited, right? In terms of degrees of freedom, which exist in an atom, or more importantly for molecules. So I think it's sort of a trade-off and balance. But I'd like to make one issue, perhaps there Barbara and Arghavan can say something. DFT was obviously developed for fermions, right? Electrons in atoms and molecules.
Yeah.
But they're not very readily usable for cold fermionic many-body systems. Right? There is a reason for that.
Is that true? I don't know.
Yes, it is not. Did you hear any of our...
No, I mean, is it not because people haven't done it, or is it not because it can't?
No, Matthias Troyer has tried,
Oh.
but there's a substantial obstacle.
It's a matter of accuracy, right? So the accuracy is not sufficient for so-called atom applications.
Did Barbara have a comment on that specifically, or? The question is sort of directed towards you, and you haven't spoken up yet in this panel, and you may have some comments out of your own many hard problems that you've tried with Monte Carlo, or you've done a lot of bosonic problems, right?
Yeah, I mean, I'm not so familiar. No, actually, I don't have the answer to that specific question. But it's true that it hasn't been used. In fact, lately, when people are trying to do cold fermionic systems and developed other, for example, diagrammatic Monte Carlo techniques, which can also deal with sign problems. I don't know if you know the specific answer to that question.
I have a comment on DFT about why DFT doesn't apply very well to these cold atom or cold molecule or quantum simulator problems. It's just because the correlation, you don't capture enough of the correlations in the density function. Yeah, it's the same reason why truncated Wigner is fine for a few things, but and it's nice when you have something near a coherent state. If you're very far from the coherent state, you get almost nothing at truncated Wigner, right?
But I mean, we heard today about Gaussian, Terracam. All of these are built upon this very, very useful and fundamental model of many-body interactions in atoms and molecules, right? DFT.
No, not necessarily. No.
Not necessarily?
No. I mean, when you do electronic structure, typically you build the whole theory on some kind of mean field theory, some kind of mean field model, but that's very often hard to
For instance,
model.
the kind of problems I presented here would not be represented correctly by DFT. Impossible.
No, I meant Gaussian.
Huh?
No, I meant I named Gaussian, not Arghavan.
Gaussian.
Yes?
The Gaussian software.
Yes. It doesn't necessarily mean you need to use DFT in Gaussian.
I think there was a misunderstanding.
These configuration interaction methods, okay, which you in other words, you have an expansion over many later determinants, okay, so you don't assign electrons to particular orbital. Well, these orbitals are represented by Gaussian functions in these configuration interaction methods. So Gaussian is a basis set that can be used with CI or in the framework of DFT. Okay.
Yeah, but I think the critical thing for the problems you're talking about is the need to represent a lot of a set of ground and excited states of the target ion, and then add the continuum on top of it. And DFT methods just are not very robust for representing excited states. That's the end of the story.
Well, it's not be arguable, but
I don't think it's all.
DFT people would not agree with this, I'm sure. But
ground state DFT, standard DFT is a ground state method only.
I agree, but I don't want to claim this so strongly, okay?
Well, somebody in the audience can speak
What
up.
I want to say is that whenever there are more than 2 electrons going around, doing things strongly correlated, forget about DFT, even for the ground state.
So may I give one example of DFT in chemistry? I think a lot of people have been working on finding good functionals to describe, say, the dissociation of something as H2, right? Or H2 plus. And even getting good functionals that dissociate such trivial molecules is not that simple, and that's of course connected to strong correlations. That do matter for chemistry, and that's why I think there's normally still an important role for wave function-based methodology. Sure. So all we call wave function-based is not based on DFT, and we'll typically build the whole configurations not necessarily on DFT orbitals. So I would say one can separate these two.
Can I go in a slightly different direction to come back? The issue of others using codes developed by yourselves. So Fernando, for yourself, you're combining Gaussian representation for the bound state together with cubic splines to build up the continuum. The number of parameters to build up a good collective basis set would be pretty substantial. If you were to give this program to me and have a go, capacity for me to make so many mistakes, how likely is that code to be run by a non-expert user?
The same as for bound states calculations. The basis set, these basis sets, what I call the localized Gaussian basis sets, these are just, a tick somewhere. There are a few ones, so you don't define them by hand. There is a manual that tells you more or less what is the kind of basis set you need. So you have to think about it. So that's why in quantum chemistry, other chemists, organic chemists, use them. And they don't make too many mistakes because it's just it's like a Windows thing, almost. So in the case of, of course, the additions we have done. All you have to define the monocentric Gaussian basis. You don't define it. You just it's just something that is fixed for most molecules we have investigated. So in fact, this monocentric Gaussian basis is the same for pyrazine as for nitrogen.
Is this like based on sort of a geometric progression to the X?
Exactly. It's a geometric progression. It's defined automatically. It starts at somewhere that is the smallest value of the exponent we can use without running into problems, up to the largest one. Okay, so this you don't touch. And concerning the B-splines, they are generated also automatically, and the only thing you have to define is your R0, this radius. And this depends on but there are, this is something you have to play with. for instance, by plotting the electronic density, and you see what is when the electronic density that comes from the polycentric part is practically zero. So you look at that and you define an R0. And then try another R0 just in case. And that's it. So the way it will be used will be exactly the same quantum chemists use their codes.
So
you will be able to do it.
okay, so I think Christoph had a question.
So I want to go back to the question of DFT. So standard quote-unquote DFT is indeed ground state theory. But if you agree that time-dependent DFT is also DFT, then of course it can treat a lot of excited states, and in some cases it is competitive to equation of motion coupled cluster calculations, so it's really not bad. But it cannot treat all states, so double excitations is an open problem. Some people work on it, but it's not yet solved. So in cases like we've discussed, when you want to have the whole spectrum of states, MRCI is the only method which you can use, really. And of course, for those singly excited, actually, time-dependent DFT will be much better, but it won't give the whole spectrum.
So out of the 4 people presenting, there was one person who was combining all of the second quantization sort of discussion, right, of our first speaker, and a lot of discussions that we're having right now, and that was Johannes. So maybe he can comment on trying to put together, MPS methods with, atomic structure and sort of other, sort of ideas, but applied to these pretty difficult molecules.
Yeah, I mean, I have to say in that sense, for example, we're using, also answering in some sense Klaus's question from before. Right now we're not in the stage of actually that we have packages that we are writing. We're using exactly all of the packages that the other communities has written. Mm-hmm. And for example, for the molecules, it's great for us that there's so much work in quantum chemistry and without the quantized field, because we can use all of that. And if GROMACS didn't exist, we couldn't have treated the polaritons with classical nuclear dynamics that give us the bars, the kind of, in the open quantum system, we're not there. There we're coming from the MPS, and the MPS there's some libraries, but I think they're not anywhere as far developed as the quantum chemistry, because the problem is maybe not so well defined and it's a newer method, but I think people are working on these kinds of things. And for example, the kinds of problems that Arghavan was talking about are exactly the same kinds of problems we were having when we were treating simpler models, that sometimes you can use the decay superradiant state, but then you put in some decoherence and you cannot anymore, and the system becomes much, much larger, even when you use very simplified models of the molecule. So, kind of also to answer your question, for what we are doing right now, I don't actually care too much about the precision of the quantum chemistry that I'm using, because I'm trying to understand what can I do in general with more or less the surfaces that real molecules have. But I don't care if that surface is shifted by half an electron volt or not. As long as the structure is more or less something that I can do and I can understand what physics can I do or what chemistry can I do, how can I modify a reaction pathway to go to the left or right. Maybe what I'm treating is not the real molecule, but the molecule that is treated with DFT and that doesn't exist in reality in some sense, but it's not going to be so far from what real molecules do. And as we've heard, there's so much complexity in the system that I'm not going to treat the full system anyway. So in some sense, that means I have very relaxed accuracy constraints compared to saying I want to calculate some excitation and get some resonance right within half an eV or within a milli-electron volt. I don't need that here. So in that sense, I think it is very useful that there are all of these works, even for all of these codes that may not be the best code available, but that is easy to use.
That's, yeah. So I think question.
Yeah. So I'm a chemist, I guess, theoretical chemist. I think you talked about an isomerization induced, and they're just 2 isomers. And what if you had 5?
Yeah, that's exactly.
Okay, so that's stimulated to ask that based on your comment. So if it's 2, you've got a good chance of getting it qualitatively right with a not terribly accurate approach. If they're 5, and they're within half an EV of each other, which in chemistry they could easily be. And as you get to more complex molecules, many isomers are present, and that's kind of the fun of complex chemistry. And now, you know, you're in a bind. Because if the experimentalists, their goal might be to determine what we call the branching ratio into these 5 possible, or maybe it's 50 possible isomers. You know, protonated water clusters are a great example that are occupying an awful lot of literature in chemical physics. Many, many isomers. If you take a proton and surround it by 5 water molecules, tons. And we're fighting, you know, in the literature about which method is going to predict the branching ratios. And it's clear you've got to do a very good job on both the electronic structure and the dynamics to be on the same page. So I'll talk a teeny bit about this in my talk. So don't disagree with all of what you're saying, but you know, as we get into more complex chemistry, we are going to be faced with this problem. I'm sure you agree.
100%. My point was more like, for now, we don't even know if it's possible with this method to, for example, control a branching ratio. So I want to find that out with any
Absolutely fantastic. I mean, I just love your talk, and I love the new directions this is taking. But you know, the poor chemist eventually going to have to get it and use it in these other ways as when life gets complicated.
Okay, so I think Barry had a comment earlier. No, you're good now? And there's a question back here.
Just a question. Stitching the codes together, software. I mean, chemistry is clear. There's prescriptions how to use it. It all works beautifully. What about the other pieces? What defines a code that you found easy to use? What do we need, or what is it worth to try?
To give some example, I mean, for example, for all of the quantum optics stuff that we are doing, it's extremely useful that there's this Python library called Qtip, that basically any simple quantum optics Hamiltonian you can think of, you just write down in 5 lines, you say, calculate a steady state, do time propagation with this field. It even does block red field for you, so you say, I have a bath with this spectral density, couple it to that. So this is, I mean, this is a jump in productivity that for the students in 1 month, they're doing what if they had started from scratch, they wouldn't do at the end of their thesis.
And who wrote that? And how many people were involved?
This is originally 2 people, I think, or 3.
I think it was in Franco Nori's group.
Yeah, exactly. It was from Franco Nori, Johannes, I think is the name.
But they have regularly dedicated postdocs even that maintain this.
Yeah, now there's a lot of people contributing, and it's actually starting to grow. It's not a very old code.
If you want to see a good model, for example, we have a look at that.
You guys may have just download Qtip. You can get it running in like 20-30 minutes. I always have my students run through that. By the way, it's not the most efficient code. It's easy to make things that go faster. It's easy to write things yourself that are better.
Productivity is what matters.
This is the point.
Yeah, I mean, all my students now use these Jupyter notebooks. I mean, you do it, you do the plot, you have in 10 minutes, you solve the James-Cummings model.
Yeah.
That is the basis of what we do, basically. It's really cool.
So, obviously we can all write better numerical methods than, you get push button out of MATLAB, but having MATLAB around helps students out. In Mathematica, this is sort of the Mallory Mathematica of quantum physics. Actually, it's the only code that's like that out there. That's what I'm emulating personally, so I give that as a good example. Yeah, but it's really for the few body problem, right? It's not really. It doesn't have MPS or things, at least not that I saw.
So, for example, for MPS, there's a lot of libraries, but there, I mean, we looked a bit. I'm not an expert at all. I don't know if they're very good. You probably.
Well, I think
coming
yours
soon.
is the best. No, I mean.
Mine's the best, but it could not as good as that.
Which is
which is yeah. So but there are very nice libraries if you're into coding, and this is called iTensor. So there's mine and there's iTensor. But as an example, the quantum chemistry codes that are all standard, everybody in the audience knows, nothing we're talking about is at that level. So there's Qtip, there's iTensor, which is from Steve White's group, I guess, more or less than other people. And then there's my open MPS code, which now uses Python, and next thing is Jupyter Notebooks. We're doing that now. So. But runs Fortran underneath it. But even those codes, like the problem is that this is why I wrote this up here on algorithms. The difference in near finalized algorithms, right, where you know the algorithms and you just want to do the best possible code implements those algorithms versus matrix product state methods where the algorithms are constantly changing, actually. You know, so you can get factors of 5 or 10 pretty easily, but just shifting algorithms, which can make the difference, right, in what you're simulating. That could be another 3 qubits. That could really matter if you're only simulating 4, right? So
I mean, to say with the code we're using now is a MATLAB code that the student of Alex Chin wrote based on the code of another student before. It's extremely complicated, but it's in MATLAB. It's almost impossible to get into. The student, of course, since he was a very smart guy, now is working on artificial intelligence in some startup. And I have a postdoc who's struggling to try to
I think it's
reuse that code. So
I think handing the code down.
That's the problem.
I think it's because it's actually like I am leaving this group and they want me to teach some other person, and it's very, very hard to hand down codes.
yeah, we're like at the DFT stage of pre-Abinet, VAST, everything else, you know. So, okay, so I wanted to make sure that Barbara and Bala had a chance to participate in this discussion, and you guys may have some thoughts or comments in relation to the 4 speakers. And after all, you're sitting up here, maybe you have something to say. So.
Yeah, no, actually, I had a question for Johannes, and it's a little bit related to what was asked by the chemist. But so at the moment, so you said you don't care about accuracy. Well, okay, just to quote you, but so how do you decide whether you're doing a good enough job with your simulations? So, or so where do you just quote, because you said, okay, maybe I'm simulating a molecule which is not existent. So how do you quantitatively know?
I think
you're doing a good
basically
enough
the
job
answer is
for some experimental.
right now we're working on a qualitative level much more than quantitative. So we are trying to understand qualitatively what can we possibly do, and much more than quantitatively how much does a reaction rate change. And I want to find out, can I change this type of reaction, or can I change this type of energy transport? And then I don't care so much right now if it's 20 nanometers or 30 or 40 maybe, that I can get kind of a transfer. And I want to understand, is this process important or can I disregard it? And there's a lot of questions like this that are still far from saying I want to have a number to say you should get exactly 10% of the emission at that frequency and 30% there. I want to know, do I have emission at that frequency at all, or is this a completely closed channel, and things like that. So in that sense, right now we're not in a stage where our simulations are anywhere close to giving numerical accuracy or quantitative accuracy for an experiment.
So do you have so for example you find okay, this is qualitatively interesting result.
Yeah, for example.
So how do I go forward now? So how
for example, the suppression of photochemistry. Yeah, the suppression of the photoisomerization that we found is very general and doesn't really depend on the exact structure of the surfaces. So you can say, if I do this, it should work with almost any molecule where the ground state is kind of it's a relatively deep well, and then I don't care if that well has a frequency of some vibrational frequency of 200 millielectrovolt, 150, because the concept works in both cases.
That's a bit property dependent.
Yeah,
you found this and said,
yeah, but it depends. It's very far from kind of. It's not like what Robin was saying, that you say I have an end-to-end simulation where I say here's my beam and here's my code, and then here this is what you will get in the experiment. It's more like what toys do I have to, what observables do I have.
So this was something in common between both of you guys, that you were exploring like lots of different methods, because it's not even clear what model or what method would be representative of the experiment. And it's highly tied to experiment, but you need to have a flexible package that allows you to explore, for example, truncated Wigner versus MPS versus, and not have to have a student write, 13 codes, because you don't know which one you need anyway, right? Yeah. I should mention here that there is one more. I actually don't like it even, and I participated in it, so I'm as guilty as anyone else, but it's Algorithms and Libraries for Physics Simulations. So ALPS. This does have this is like the kitchen sink code for quantum many-body stuff, but it's quite hard to use. So essentially only the developers ever really use it. I'm one of them. There's about 20 of us. Well, I mean, I like it for myself, but I recognize that it's not very useful for
Yeah.
other people. So that's why we developed something, working on something different. But I just didn't want to leave it out because, you know, it does really have everything. It has Monte Carlo, it has
Yeah.
exact accusation, it has everything, right? But it's way too much. It's like 5 hours just to compile, okay?
Really?
Well, because it has everybody's codes combined. It's just the design, okay? I don't want to get into it because I'm just supposed to moderate here. But anyway, we put it down in 2012 or something. Okay. So, Bala, did you have any?
No,
feedback?
I'm here. I think I just happened to be in this panel because I was chair of the previous session. It's actually over there, and Raman, you should be actually on this side because you are in this panel. But anyway, I think just after listening to the really exciting talks this morning. And within the spirit of this workshop, like, say if you want to go to the next step and really produce some course that would be of use to the broader community, and what it would take in terms of from the funding agencies, because this is an international group here, so I think it would be even good to know. I mean, how is it in your in terms of the funding sources that you have in Europe, how they support this kind of activity? Because in the U.S. there is this issue of when you are doing a code development, where NSF always weighs the intellectual merit versus the broader impact aspect of it, and it's always one has to walk a very fine line between the two, and if it is not strong on both sides, and sometimes we write proposals and we review proposals, and I think that is the one point I think you should address at this meeting.
We have NSF people with their hands
Yeah.
chopping up.
Well, I
Hi,
mean,
Mrs. Bellman.
well, okay, so I would just say that there's, someone mentioned Balakrishnan Mahala, and he runs the computational physics part of the physics funding, and he's been trying to work with, and some of you who get funding from that, to work with people to go from exactly this problem where you're working on something, you want to try it out, you see how it works or it doesn't work, and then when it goes beyond, so now you're actually going to go and say, I'm going to make a tool for the community, then you move into funding that's not from the physics division, or maybe only partially supported from the physics division, but now we start bringing in the computer science, whatever it's called.
Office of Advanced Cyber Infrastructure. OIC.
Yeah, so maybe we keep changing the name. So I mean, that's a you're going cross columns at NSF, and it's a personal. It's bogged in working the system sort of thing. But there have been successes along that line. So it's possible. I'm not saying it's easy, but there is funding to do that.
So I mean, so let me just go and comment. I think to try to, this is me speaking, to separate program development from theory is, I think, a mistake. I think if you look at a lot of how quantum chemistry codes develop, you'll see there's always been an interplay between fundamental theory and the development of the codes, right? I mean, and I think it's still there today. So I don't just look at it as code development.
But there's a difference between me writing code that I'm going to use, which, as Tom Rosigno would say, gives me job security, and something that I can give to someone else. I mean, there's a difference there, and also, to run something that's good enough for what I'm doing compared to running something that is efficient and is using the best algorithms. I mean, I'm not saying you have to have that interplay, but I think at some point it's good to get on the computer side in on it.
But a lot of the larger efforts which are ongoing and supported in a sustained way, have people in those efforts who are doing both things. It's constantly evolving, and they're releasing new versions of these things which have new physics in them. And so that's what I was trying to say.
I guess my actual talk is at the end, so I'll report on making that bridge and how that works in some detail at that time. I wanted to make sure that, Roman, I somehow didn't realize that you were in this list when I
right.
called people to the panel. Can you come take this chair?
I'm more comfortable sitting.
Oh, you're more comfortable. But now we'll all just try and look at you. But could you maybe comment on some of these issues or respond to some of these things that I've written up on the board? And those of you sitting here might want to just glance back at some of the things I've written down about what you've said while Roman speaks.
Well,
So,
actually, I had a question for Robin that I was waiting to ask. So, are you satisfied with the precision of your calculations? Currently, and if not, what are the next steps? What are the challenges that you're going to be facing to develop those tools further?
So I showed you, for example, only atomic fragments, which arise in the focus of the beam, but once you break up into lots of molecular radicals, all this force field type stuff is just bad. And it's I can't put it any other way. So you cannot describe any of that very accurately. I must also say whether it matters for bioimaging is a different question, because the image formation happens during the 10 femtosecond pulse. So whether you're not able to describe the fragmentation afterwards, maybe it doesn't matter so much. But if you're asking whether people aren't looking for the fragments, then the answer is, of course, no. People are looking for them. People are performing basic chemical physics type experiments in such systems. And I would say, by and large, we're not able to describe a lot of what's going on there. Then I mentioned to James Colgan that I think basically relativistic effects tend to be important, especially when you have heavy atoms involved in the molecular species. And to get that right, proper molecular relativistic electronic structure for a whole family of excited states is not trivial. Another thing I mentioned, that we do SCF. Well, we do not ground state SCF only because we keep stripping away electrons from inner shells, so we do excited state SCF all over the place, which sometimes we do kind of a maximum overlap philosophy, where you're assuming initially you can get your SCF converged, and as you're moving through configuration space, you're always starting the iteration with that previous state. At some point you find that the SCF solutions disappear, and then you get very annoyed, and then you have to basically find a way in configuration space to still find a suitable solution. So I would say there are lots of practical questions. Many of them, I would say, when you're talking about matrix product state techniques, those are techniques for strongly correlated systems. Such techniques are nowadays also kind of noticed by the quantum chemistry community. So I think there are also opportunities for cross-fertilization in these areas. And as I said before, a lot of that has to do with properly being able to describe dissociation of molecules. We use naive SCF. We're not dissociating molecules right. Even if we're not just using force fields, we're typically also not dissociating them right when we're doing SCF. Hard-translated type SCF. So all these energies are just not coming out right. So if you're asking me if we're really trying to describe the chemistry, I would say, oh gee, we're really not doing particularly well.
Is it ever going to be feasible?
I do think so. I think for small systems, yes. And maybe at some system size, if one can describe the system as a sum of subunits, and in each subunit you can do a better job than for the whole system right away, then I think so, yes. Doing it stubbornly with one technique for an increasingly complex system, probably no. So I think there's still a need for flexibility here.
Yeah, and this is a very good point, and the reason I'm asking is because there's of course a cross-link between the Hamiltonians that Robin is studying and the Hamiltonians of Arghavan. Like you could map the quantum chemistry Hamiltonians onto the graph Hamiltonians, and then once we develop quantum computers that could explore those graph Hamiltonians, then we may be able to go back and do make some of the problems that you just mentioned.
This is exactly what I was going to comment on. So if you look at the like the IBM demonstrations of of things for quantum chemistry, they're extremely simple things that who cares, right? I mean, it's just a point of principle, proof of principle or something. But if you can get this mapping going properly, you can, as I wrote up here, get first and second quantization sort of talking to each other, and use these second quantization based quantum simulators to give information about excited states, ionization, complex chemistry problems, etc. And people really haven't done that work. So one of the overall questions that I think comes out of these conversations is, to what extent can some communal software effort enable foundational science, as Barry put it, fundamental science, as far as getting really high accuracy calculations of things in chemistry that we just can't get on a classical computer. So that mapping could happen if people had those sets of tools available simultaneously and got them talking to each other to some extent. So I think there really is something beyond just the software tool and related to AML pretty specifically. And I think you guys know much better about this than me, but I'm just summarizing essentially what Roman's already said. But yes, comment please.
Yeah, I think a comment has been brought up yet. We say it can't be done on a classical computer. Well, classical computing resources are growing exponentially, right? Like, imagine Titan could get a fraction of Titan. Could some of these problems be done? Assuming their code was, tuned up, ready to go. And pretty soon, some of it will be available.
So the usual sort of silly number is, if you have 100 qubits, if you have a Google, right? Then you're done, right? I mean, you can never do classical computation if you're using the whole Hilbert space.
Right.
Yeah. So to do an extreme example, which is probably unrealistic. So you get a few more qubits, you can go a little bit further, but a great example is the open quantum systems that were brought up by several people.
It's not real qubits. It's all the other qubits you need.
Yeah, the error correction.
Yes,
for example.
that's the problem.
Oh, I understand. I said an
I know
ideal
you
example.
but some people may not.
All right. So go ahead.
There's not much AMO community work being done on these big machines.
Yeah.
Not a lot. I mean, they're always trying to get.
Oh, you're talking about like high performance computing on classical computers.
No, that's very true.
Neuromorphic computing, other models of computing, for example.
You don't mean that. I think you're talking about just even in general.
I think it means it's sort of petascale, very large machines like Hadoop grids and Arghavan and so on.
Yes, there are not very many. I mean, I know this quite well. There are not many big users in the AMO community who use the big NSF machines or the VOE.
But that's because a lot of the computational chemistry codes don't scale to the 10, 100,000 types of processors.
That's part of it, but it's not the whole story. That's part of it.
That's part of it. So, that's a challenge for even a wider community.
Yeah. But I also, I don't know, and I'm willing to be corrected on this too. I think there's a mentality in the AMO community that they don't want to get on the big machines almost. I mean,
why would that be?
I don't know. I mean, it's like, I mean, if a problem, I mean, it seems to be, well, even we heard earlier, you made some comment of, I can't remember, you made some comment about, it was just a throwaway.
Classically computationally intensive.
Yeah, it was like, there's nothing wrong with something that's computationally intensive. If you've got to use a lot of hours on a machine, you get a lot of hours and you use machines.
I do use a lot of hours and a lot of machines.
But there are machines available to do that, and I don't think the community should shy away when they need it.
Yeah,
That's
I
all.
think the
That's all.
problem a bit there is that if you're implementing a lot of different models, and to get a big parallel code running well in parallel, it's a lot of extra work.
Oh, I didn't say no.
I mean, you know that perfectly.
Yeah.
So, but if one of my students is trying a simple model that we don't know will work, and I see, it would be nice to go up to 50 spins there. That's impossible. And he's not going to spend a year to write a parallelized code that can do that if I don't know if the model even
Yeah,
fits.
I don't know what to say about it.
So the basic
That's
answer
kind
is
of the problem.
data parallelism is obviously trivial and we can all use that. But beyond that, it's just a lot of work when you don't know what model you're going to use anyway, right? Or what method is the best method. That's the problem. That's
But
not
I'm
on
sure that people are not. You're not. I wouldn't assume that people are working on one method at a time either. They're probably working on a number of methods at the same time, right?
The amount of students I have
Okay.
Several methods in parallel machines.
So we're already at noon. Mike, do you have a quick question or comment you want to make?
Well, I just wanted to make a comment. I remember Barry saying at the beginning of the session today that
The AMO community has been somewhat slow in trying to develop some of these common procedures. And I guess a lot of this discussion reminds me of why the AMO community is slow in comparison to some other communities. It's very, the problem has been around for as long as since I was a graduate student, that when you have physics operating on different physical length scales, or different energy scales, or different time scales, then incorporating them into one, bridging the gap and incorporating it into a single physical theory is a difficult thing. And that seems to be something that's intrinsic to this community. Everybody, in some way or another, is working on just those kinds of problems. That's what makes AMO so challenging and so interesting in many respects. So I think that what gets me is that 30 years ago, people were talking about similar problems where you have physics going on multiple length scales. What's changed now is, of course, the resources are much bigger than they were before. And I'm just wondering, are we really at the level now where the resources are sufficient that we can talk about and develop things that can really be used to handle problems where there's intrinsically much different physical length scales, much different physical time scale, and where we can really just clobber them with computational resources that are big enough to do that. If that's true, then certainly you can see that some common resources could be developed and be useful to a lot of people.
And so there is a place that does this really well. Actually, this happens in condensed matter too. It's not only in AMO.
Yeah.
And so that's NanoHub. So if you haven't seen this, you might want to just have a look. It's a collection of all sorts of methods, but it's a nice clearinghouse for like all the codes, treat all the different device problems, and it's very similar to the sort of thing we're talking about in many different contexts. And some of them are small and some of them are big, and you can grab what you want. And you know, that would be the dream, is to have something like that would have all these methods together. Right?
I'm not familiar with that. Could you give me a few examples of what that?
It's a very well known.
Yeah. So just
gateway.
how about just click on it tonight, and then is it okay, Barry? And then we could, or even over lunch or whatever, and then we could talk about it. But it's actually the biggest science gateway in related to physics out there, and it covers physics, material science. You know, there's a lot of toy models. I don't know. You wanted two couple quantum dots, you could do something about those, or you know, you want to have device design for your semiconductor, and you know, have different layers. You can kind of model that. It has like a lot of different. It's literally hundreds of codes in there. So
and I think it actually does not run on very powerful machines. It runs on fairly.
Oh yeah, you can actually run it over the internet. Some dedicated resources. Anyway, so let's come back to that because we're already at noon. A quick comment from Robin, and then we should probably stay on schedule for lunch. But yeah.
So I just wanted to come back to an earlier point that you made, the mapping of, so to speak, the type of electronic structure Hamiltonians that we have to the type of model Hamiltonians that AlterCode community looks at. I think this is a great goal, but I'm wondering to what degree such mapping can actually succeed. We know how to write our own Hamiltonians in second quantization, and we know already the complexity. The one particle basis is essentially for us, continuous. Right? We have a couple of bound states, and we have a lot of continuum in which the many-body system has to evolve. I think the mapping to the types of very discrete Hamiltonians that I think the AlterCode community seems to be using is not so obvious, and as I said before, the AlterCode Hamiltonians, I call them that, are meant to be effective low-energy Hamiltonians. We typically pump into the system quite a bit of energy. We're not actually trying to be close anywhere to the ground state or anything like that. We're heating the system quite considerably. So I think this mapping is an interesting goal, but I think this is going to be an enormous challenge.
But that's exactly the point. You're mapping your Hamiltonian that involves high energy states onto a Hamiltonian that's effectively a low energy Hamiltonian. That's the whole idea. And then you can look at that Hamiltonian in the discrete representation and explore which parts of your Hamiltonian.
You're just
are
saying that in
compass-based,
words.
right?
You didn't tell me how to actually do that. What I'm saying is I don't believe in the mapping.
Can I just give one concrete example, and then we can close with that and continue? Is that okay? I don't know who's leading things, but.
The chairs over there, you're the discussion.
Yeah, fine. Is it okay with you if I just?
You are the discussion because so it's all completely.
Well, I just want just so that
We don't have to break for lunch, do we?
Well, some of us eat, but so I just wanted to comment an example, and so it turns out that if you start using these many-body Hamiltonians for AlterCode systems to try to model actual things in experiments, the discretization schemes are not very clear. A great example is the Bose-Hubbard Hamiltonian. So you take Bose-Hubbard Hamiltonian, which is sort of the default in optical lattices, and Roman knows this, so just to make it clear for everybody else. So you have just atoms moving from site to site, and you have on-site interactions. The simplest possible thing you can have beyond single particle physics in the many-body problem for bosons, right? So now you ask, okay, turn up the interactions between the bosons, or have anything happen that's interesting beyond, some sort of weak interaction. And you find out very quickly, if you're trying to model the continuum, you need thousands of sites if you want to catch like 5 bosons, for example, interacting strongly. So there are some wonderful groups that have compared this stuff to multi-configurational methods, right, in Heidelberg and other places, and tried to understand that connection. And one of the problems is that Bose-Hubbard model, you could put in more terms into it, like longer range terms, that would fix this problem. People don't. They just use the simplest approximation because it looks like the experiment, right? Most close to the experiment, huh? And that makes it very ineffective for problems like this. So you actually have to modulate what you're doing with the quantum simulator platform, right, to turn on to so-called extended Bose-Hubbard terms. I'm just trying to answer yourself concretely, so it's not just words. Hopefully this is working. Okay, so you have to turn on those extended Hubbard terms in order to get a more efficient discretization scheme so that you can capture things like stronger interactions or excited states.
Long range.
Longer, not only longer range, and just stronger interactions. Like TAMP speed specifically, I'm thinking a TAMP Jardot limit, okay? Which you can improve the Bose-Hubbard Hamiltonian exactly fails to capture because your density goes to 0. Anyway, I showed on the board at the break if people would like. So I just want to make a comment that what happens is, things like molecular structure calculations or ionization calculations, etc., they require the quantum simulator platform to work in a different regime, right? And so that is a piece of crosstalk, right? It's not like you automatically get it in the regime they're in right now, yeah? And that's a very important piece. So that is fundamental science that needs to be done. So that's what you're sensing. So I just wanted to end this panel with that comment that there's an opportunity for great dialogue between the couple of fields, the second couple of fields, and the first couple of fields. And somehow Johannes was trying to do it all. It was very courageous. Okay, last comment before we go to lunch. Yes, Hossein.
May I volunteer Lincoln to give us a demonstration after the afternoon session in this nano hub?
Oh,
what nano to the internet?
I'm sure we can just jump on the internet and play around with it. It's just you grab some pull-down menus, or maybe I can do that during my talk on Wednesday if you like. I mean, it's up to you. So yeah, it's totally not a big deal. You can even grab some things on your phone. Like, it's really easy. Okay, it's just like click. I'm not sure you need me to do that, but I'm happy to do it. Okay. Thank you. So,